Okay, so in the second half, we're going to, not yet this one, we're going to deal with something called cumulative distribution function. So it is a little bit different. Okay. Okay, so in the first half, the kind of questions that we were dealing with was like, what's the probability of getting exact number of successes? Right. So previously it was getting, if you were talking about getting one success, is PR x equals 1. Now this question is a little bit different. This example, the probability that a person currently in prison has ever been in prison before is 0.72. That is telling me that the small p probability of success is 0.72. Okay. Now, of 5 prisoners chosen, that tells me the number of trials is 5. Right? At least 3, okay, this is the key word here. At least 3 have been in prison before. At least 3 means 3, 4, or 5. Right? So how do we represent this information here? It's not just one number, right? It's not just x equals to 3. It's x equals to 3, 4, or 5. So technically, this is the probability of getting 3 of them to be in prison before, plus the probability of 4 of them being in prison before, plus the probability of 5 of them, right, have been in prison before. So technically it should be this thing. Is there a shorter way to write this? The answer is yes. Probability, so this is the meaning, right? But the shorter way to write it is probability x is, guess what? You can use the greater than symbol. Greater than or equal to 3. Make sense? Yeah? Because all these values, 3, 4, and 5, it's just simply at least 3, right? That's what means at least 3 is. Now, be very careful. So, if you have, so let's say at least 3 is the same as more than or equals to 3. Right? If it's more than 3, would be, so this one would be strictly more than 3. Here's a colon there. Does it make sense? Yeah? Or less than 3 would be this, less than 3. Right? So just be very careful with the word at least. It means it's inclusive of 3. That one is the only one that has an equal here. Right? Otherwise it might be like, less than or equals to 3, but normally don't say that. It's either say less than 3, more than 3, or at least 3. Okay? So, how do we do this? Probability of 5 chosen appear x equals to 3. So technically you will need to write the expression, which is equals to whatever that thing is. Okay, so PR x equals 3, and then plus. Now a little trick is you can write dot dot dot, and then plus PR x equals 5. So it's saying all the values between 3 and 5, because sometimes you don't get a short range like 3, 4, 5. You might get 3, 4, 5, 6, 7, 8, 9, 10. Right? So you write probability x equals to 3 plus dot 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 PR x equals 10. Right? So it's saying that it's all the values between 3 and 10, for example. In this case, it's all of the possible number of successes between 3 and 5. Okay? And after that is using GC. Now, how do we use the graphics calculator? It's almost the same as the steps before. Okay? So it will be almost the same as this. Alright, I can even copy that down here. Alright, the only difference is the next step, instead of going to binomial PD, you know binomial CD, cumulative. So cumulative is when you have a range of values. Okay, so Peter, try it. Menu, statistics, try it on your calculator, distribution, and then binomial, and then BCD, and see what they ask you.
Distribution, B.
CD.
CD.
Okay, so you see they ask you for a few things, right? They ask you for the lower.
Is it 3?
Yes, lower would be 3. and upper would be 5. Yes, that's it's essentially the two values that you were writing over here, right? Start from 3, ends at 5. So lower is 3, upper is 5, and then the rest is the same, right? Trial is 5 trial, and then success P would be what's in this case 0.72.
Wait, can you say it again?
Right. So the number of trials is 5 because there are 5 prisoners, right? And then the P or the probability of success is 0.72, which is a probability that someone has been imprisoned before.
Yeah.
Yeah, and then press enter.
0.8624.
8624. Yeah, to 4 decimal places. That's the correct answer. That's it.
Yeah.
Okay. So the only thing that's a little bit different is, so I'll just put the notes over here. The only thing that's a little bit different is you have to write like what is the range you're working with. So first you need to interpret the right range and then write out what is the range. And you're just adding all of them together because it's all, right? 3, 4, or 5. That's why you have to add the probabilities together. Does that make sense? Start adding, yeah? Okay, so yeah, so that's example 3, and now we can actually start looking at the other exercises. Right, 7. Okay. All right. Fair die is rolled 6 times and the number of 2s noted. Find the probability of exactly 3 2s. So if you were to write out the steps, right? This one, A would be PR x equals 3. The second one, PR x more than 3. And then the third one, PR x is more than or equal to 3. So remember, reading this one, just be careful, yeah? 3 is the number of results. 2 is just like the condition of success. It could be a bit confusing. Yeah? Or more than 3, 2 is like what? But it's just more than 3 and this is success. So I'll read this one as more than 3 successes and then at least 3 successes, right? Because the number of 3 is noted, sorry, number of 2s noted is the number of successes.
Yeah.
Okay? All right, so Peter, try this one out, and Stephen, if you're listening, try this one out as well on paper.
Is that A?
Write it out properly. Alright, so work through this question properly.
It's a complex family. That's so easy.
Yeah. This chapter sort of feels like that, yeah. The real complex one will come in after this one. It's a conditional probability stuff.
Is that the P one is 2 over 6, is it right? Cool.
Which one?
The P.
1 over 6.
What about, let's say, the number of?
Yeah, the number of 2s noted. So the success event is getting a 2.
Oh, the 2. Oh.
Yeah, and success equals getting a 2, right?
And that's like 2 times or something.
No. That's why you have to interpret these ones carefully. That's, I guess, that's the complexity of it.
Yeah.
Yeah, got it?
Yeah.
Now, Peter, what do you notice about these three answers? These three values, what do you notice about them? The answer for A, B, and C, the numbers for A, B, and C.
Should be the answers only.
Yeah, just look at the answers, right? The one in the boxes, like this one, and then this one. What do you think is the relationship between these three numbers? There is a relationship between them. In fact, you can get one number from the other two.
Actually, like I think the higher of the higher chance of getting more. There's lower chance of getting more twos.
Yeah, there is lower chance of getting more twos, you're correct. Right? So that is correct. This number is the lowest because you're trying to get 3, 4, or 5 twos. Right? So even if you add them all together, it's still a low chance, yes. Yeah. But how about this one? And I'm talking about the relationship between these three values here.
Oh, so I think you add up those two together.
Yes.
You get that one.
Yes, when you add these two together, you get this one. But why?
Because this one's 3 and this one's like 4, 5, 6 already.
Yes, that's right. Yep, very good. So the idea is, and this is actually important for one of the questions later. So the idea is this. If you're trying to find the probability of x is more than or equals to 3, right?
Yep.
This is technically 4, 5, or 3, 4, 5, 6, right? And then the probability of x is more than 3 would just be 4, 5, 6, right? Which means when you plus this with the probability of x is exactly equal to 3, it should be the same as before, right? Because then it covers the 3 as well as the 4, 5, 6, right? 4, 5, or 6 successes, okay? What does that mean then? When you, okay, actually, I think I'll pause here, see if you can figure that one out. Question 8. Alright, question 8 is the interesting one. The hint is there is a very easy way to do question 8b2. Okay, so see if you can work out question 8. The general rule for the probability distribution of the number of winning tickets is just saying probability x equals to x, and then that will be something. Right, fill in whatever you know, but the number of winning tickets is, this one would be x, and you don't know what x is, but you know everything else. Yeah?
P.
Okay, maybe I'll show you the answer for this one first, because there will be a similar question later. So what's the general rule here? How many trials?
10.
10. So 10x, because you don't know how many winning tickets, right? Yeah, but you know the rest of it. What's the chance of winning a prize? 0.1 power x, 0.9 power 10 minus x. This is essentially the general rule. Okay? Now, E1. Use the rule to calculate this and that. Hint, this one will have to be, let me see. This one you can do without a calculator. Most likely this one will come out in a non-text
So
paper.
this one just like 0.9 index 10.
Yes, that's right. Yep. So question I, probability of 0 win, right, would be 10, 0. That's only one way. And then that would be 0.1 power 0 with no win, which is just 0. So that should be 0.9 to the power of
Oh, I get it, yeah.
10.
Yeah.
And you can't work it out, right? In the tech-free one, just leave it as it is.
Yeah.
So how do you find question B2 then?
Is it 1 take away 0.9?
Yes.
Index 10.
Yes, very good. Okay, I think you are one of the few students who actually figured this one out at this point. So x is at least 1, so more than or equals to 1. This is the same as 1 minus x equals to 0. Yeah. Okay. And why is that the case? I'll give you a formal. Definition, right? If there are 10 wins, so you can have either, if there are 10 tickets, either 1 win or 2 or 3, or keep on going until 10, and you could only have 0 as well. the probability of x more than or equals to 1 is these ones, right? But note that the total probability is equals to 1, right? And so that the probability of 1 or more, so 1 all the way to 10, it's just simply the whole box, which is 1, minus the probability of the thing that's left over, which is probability of x equals to 0. Yeah. Right? So think of it as like the box theory, where the right side of the box add to the left side equals to 1. So you want the right side means it's 1 minus the left side of the box. Right? So yeah, so now that you've known that, the answer is just 1 minus 0.9 to the power 10. In the tech-free paper, you just leave it as that.
Oh, yeah.
Right? So that's all I want to see. You don't need to calculate 0.9 power 10. But most likely in a tech-free paper, you won't see 10. It will be like 3 tickets or like 4 tickets or something. So you have to calculate like 0.9 times itself 4 times. Yeah, to get some sort of value. Okay, if they really mean they could give you that. But yeah, but otherwise with the calculator, you can do it the normal way. And you can also just calculate what that is. So 0.9 to the power 10 would be, so that one would be 0.3487, right? And then 1 minus that would be 0.6513. Okay, you can even use the formula like the with the calculator. You can just use the by BCD, BPD stuff, and you should get the same answer. Okay, so that's question 8. A little bit different than the main one that's new in question 8 is this thing, where when you get the right side of the box, the entire right side is just 1 minus the left hand side. Some questions in the exam, if you don't know this, you just simply can't do it, because the if you want to calculate, like, you'll be like, wait, what? How can I do 1, 2, 3, 4, 5 all the way to 20? So you don't need to. It's just 1 minus the other side. And the complex one, it might not be the simplest one, like more than 1. In the more complex questions, you could get probability x is at least 2, right? And that would be 1 minus probability x equals 0, and then you plus that to probability x equals 1. Or you can just say 1 minus that and then minus another one.
Yeah.
Yeah, so you still have to calculate this and that, and this one you can still do, right? Because most of the time, remember how the Pascal's triangle, 7, 1 is just 7, right? If it's 7 chairs in one of you, then you can just move yourself 7 times. That's 7 scenarios, right? Yeah. So you can still do that, something like that. Okay, so this is one of the harder questions. You would see something like that in a tech-free environment. Okay, if you don't recognize this right-hand side, you can't do it, because you're like, oh my god, how can I do probability x equals to 2 and plus 3, plus 4, plus 5, plus 6? That's too much work. So the idea is that you don't have to do that. Okay, all right, and you see this concept again and again and again in the next few chapters. But let's try question 9 here. All right, work this one out on paper. Alright, I'll start working through this one now.
Can I put my answer in this? Because it's gonna be that number.
Oh, I see. Just use that one. Just use the 2 point something times to.
Is that right?
Yeah, just use that one. Should be okay. I think the textbook would be the same answer. Wait, shouldn't be that small though. Answer shouldn't be that small.
Because it's like 0 that number. So it's gonna be 0, 10, and 11 there.
No, this one is 0.8. Failure.
Is that the same probability?
No, its success is 20%, failure is 80%.
Oh, yeah.
It's a 1 minus.
Did you even do this in university? Did you do this in university?
No. This is strictly for statistics students. If you do statistics in university, then you would do these ones. But I don't think you would use it anywhere else. Even in saying that though, understanding these things actually help you understand, like see the world a bit differently. Now you know how difficult it is, how exponentially difficult it is, if you're trying to expect multiple wins at the same time. So some of the business theory actually is explained by statistics quite well. And later, towards the end of Unit 4, you have to learn something that's actually very interesting. It applies to almost all areas around of like your life that you never thought about, but it's actually applicable to it. You learn that later towards the end of Unit 4. It's called sampling. Sampling. Yeah, getting a sample and doing some tests on it. Okay, so note that if you were to use number, for example, this one here, the 0.0859 again, you will need to use a higher decimal point. So I will need to write an intermediate answer, 993 with more decimal point, and then use that one first before I round it up.
Yeah.
Even though this one, it doesn't affect it because when you're doing subtraction, it doesn't change the rounding error at all. However, when you're doing multiplication, a slight rounding error might cause one of your digits to be wrong at the end. So always use more decimal place in the intermediate answer. 8993 then. So that would be 0.9141 to 4 decimal places.
I don't know, is that right? But like for my previous exam, I have like 4 decimal places for my answers.
Should be okay. Should be okay.
Yeah.
As long as you have more than what's required, I think you'll be fine. Unless they explicitly say, leave the answer in 3 decimal places.
They don't have that.
They don't have that? Yeah, they just do 4 decimal places. That's like the standard one. Okay, did you get that? 9 for 1. Okay, all right, good. Good. Now, okay, next one. We'll try one more and then I'll go to the next concept. Okay. All right, try this one. It's another one ago.
Yeah.
Yeah, you get that? Okay, good. So yeah, when you're doing probability, if it's like, if for decimal place looks like a weird number like 0.0000, go to 3 significant figures.
3.
Yeah.
So always like take over 1.
Or even 4 significant figure is okay. Whatever you can see. So you see this one? This is 3 significant figure, right? Because that's 1, 2, and 3.
Yeah.
Significant figures, because the other zeros are not significant. Right? It's just a really small number, but the numbers I want to see is 1, 2, and 8 after the zeros.
Yeah.
Yeah. So that's 3 significant figure. Rolling away. The third one, B3, is the slightly different one. On 2 or 3 days.
Is that right?
Yes, very good. Yeah, it's just or. So it's just you find the probability of 2, and then you add that with the probability of 3 days.
Can you just get straight to the answer? Or
Yeah, you can,
I need
yes.
to get
No,
two steps.
no. With the calculator, it should be like using GC, and yeah, because you can use the binomial CD, the BCD version.
That's BCD.
Yeah. Yeah, I'll just leave the parameters for the BCD here. Okay, 0.3 and 9?
Yeah.
Yeah, pretty easy, right? Okay, now let's do something a little bit harder. Conditional probability. Finally, get up to that point there. Okay, so conditional probability is arguably one of the hardest thing to get in the probability topic at high school level. It's one of the hardest thing to get. So reading this, okay, let's read this question. The probability of net bowler scoring a goal is 0.3, easy. P equals 0.3. Out of 6, yep, that just means n equals 6. The first one, they score the goal 4 times, easy. That's PRX equals 4. Now the second one, 4 times, given that she scores at least 1 goal. So the first one is a straightforward PR x equals 4, yeah? The second one though is PR of x equals 4, and given that is the vertical line. Have you seen that? Yeah?
What's that?
The given that vertical line means given that. Given that x, she scored at least 1, so x is more than or equals to 1. So that's the notation there. How question B?
I still don't get it, like 4 times, but...
Given that. And that's why I say it's one of the hardest basic probability concept in at high school level. Now let me give you a quick run through on conditional probability. Conditional probability. Okay. Let's just say we have a classroom. Alright? And then we have a bunch of students. Now there are 6 students doing math only. Alright? Let's say chemistry, right? 6 students doing chemistry only, and then 7 students doing physics only. And there are 3 students doing both chemistry and physics. And there are, let's say, 4 students doing neither chemistry or physics. Yeah. Right? So that's epsilon, or like the total sample space. Okay, so, alright, so put it this way, the probability of someone doing chemistry out of the entire class is what? Well, there will be 6 plus 3, right? Because that's the total, that's the total circle for chemistry, right? So that would be 6 out of 20. Because there are 20 students in total. If you add them, it's 20. That would be 0.3. Make sense? Yeah? And then the probability of, let's say, someone doing chemistry and physics at the same time would be 3 out of 20, which is 50.15. Okay? So far makes sense, right? Now, given that they do physics, what's the probability? So now, given, so let's look at something, the conditional probability. Given they do physics, right? What's the probability that they also do chemistry? So this one, based on this Venn diagram, what do you think it will be?
Physics and chemistry, 10 over.
No, given that they do physics, what does that mean? It means we're only looking at these people. Yeah? It's restricting it.
7.
Yes, so now it's out of 10 instead of out of 20. Does it make sense? Because given, right, we're ignoring all the other people.
Okay.
That's what it means. Given that means you're restricting the sample space to the one that's, like in the smaller sample space. right? Given that they do physics, what's the probability that they do chemistry? Well, it's actually it's 3, yes, right? So that's 3 out of 10, which is 0.3. So how do you relate this? So this is actually, given that, okay, this is the nominal way of writing it. The proper way is actually probability that they do chemistry given that they do physics. All right, and that would be this. So how would you relate back to the main probability? Because we know probability of chemistry is that, probability of chemistry and physics is that, and then you also know what's the probability of physics only. That would be 10 out of 20, right? Which is 1 out of 2, or 0.5, right? Because there's 10 people doing physics out of the class of 20. So what's the probability of someone doing chemistry given that they do physics? So given the diagram, we can find that out. But I'll tell you the formula. The formula is probability, so C given P, or in this case, okay, the generic conditional probability formula is, let's go back here, right? PR, probability A given B is equals to, it's a fraction. It's a probability of A intersect with B, or A and B happening together. Intersection, right? Remember intersection, like C and P is they have to take both chemistry and physics. Yeah, that's the intersection over probability of B. Okay, so applying the formula, what does it look like? It means that would be equals to probability of someone taking both chemistry and physics over the probability of physics only. And when you think about it, it makes sense because 3 is like, this is chemistry and physics, right? And then 10 is the number of people with physics only. You see how it's restricting it? It's dividing by a smaller domain, right? So when you were to calculate this, so we got 0.15 over 0.5. Does that make sense?
Yeah.
Over 0.5. And I can quickly times the top and bottom by 2. That would be 0.3 over 1, which is 0.3. That aligns with what we were talking about earlier. Okay, so the intuition behind the conditional probability is that given something means you restrict the sample space into a smaller sample space here. Like in this case, we're restricting it to physics only. Right? And then you count how many people does chemistry within that sample space. But that means in the main sample space, you're looking at someone who does both chemistry and physics. For that to be in the smaller sample space of physics only, right? Because if you count these one, that's not within the new sample space, right? That's in the main one, but this one is not in these 6 people are not in the smaller sample space. So that's why it's and, right? It's given they do physics, it's probability of chemistry and physics divided by the probability of physics only. Okay, so that's the intuition behind the conditional probability. Make sense?
Yeah.
Okay, all right, good. See if it will make sense if we apply it to the question here. Well, the application, so that's the intuition, right? But the application is a little bit different. Okay, so let's say probability of x equals 4. Given that x is at least 1. So think of it this way. Out of 6 attempts, right? So you could get 1, 2, 3, 4, or 0, 1, 2, 3, 4, 5, 6. So given that she scored at least 1, we are restricting the domain to only this. Make sense? Yeah? And what's the probability of x equals 4? It's just the one value out of this. Okay? Now, okay, that's one interpretation. Another one that I commonly use is this. So first you write the rule here. X equals 4 and x is more than equals 1 over PR of x is more than equals 1. Okay, this one you can find. Now, how do we do something like this? This thing here, that's strange, isn't it? How do you do that? To resolve this condition, what I use is the number line. There are 2 conditions, x equals 4 and then x is more than equals 1. So what are the possible values here? 1, 2, 3, 4, 5, 6, right? Right? Which of these would satisfy the second condition, x is more than equals 1? It means it will be this one, this one, this one, this one, this one, or this one. Right? All these values, 1, 2, 3, 4, 6, they are more than equals 1. Make sense? Yeah. And then x equals 4 is just here. So what's the intersection? which is the number that has 2 dots? Yes, 4. This is the only intersection between the two conditions. You see it? Another way to draw this number line, look, the faster way looks something like this. The first condition is x more than or equals to 1, right? And then the maximum is 6, and the other one would be 4. So x more than or equals to 1 is represented by a dot, and then with a line, like so. And then x equals to 4 would just be a dot here. So the only part that, when you look down from the top, the only number that has a crossover between two conditions is 4. Well, make sense? So yeah, so that's why that whole thing resolves down to PR x equals 4 only. That doesn't happen all the time. Okay, that actually doesn't happen all the time. Over PR x more than or equals to 1, and then you just punch calculator, you get the two values and put it in. Just make sure when you punch in the calculator, you use a longer decimal number.
What do you mean by it's not happen like all the time?
Oh, good question. Other examples.
Wait, so what's the just that sign? You converted you.
The inverted U intersection.
Intersection.
Yeah. So maybe I'll put a note here. So this one. Oh. This one means in the section, or also means and. Yeah, so x equals 4 and x is more than or equals 1. So it's x must be the value that satisfy both conditions. Because it's an intersection, right? It's like how before, C and P, C intersect with P means they do chemistry and physics. Alright? Because it's an intersection, so it has to do both chemistry and physics. So other condition can look something like this. Condition examples. What is the resolved answer for x is more than or equals 3 and x is less than 6? What do you think? Again, number line. 3, 6. Okay. Oh, sorry. That technically should be the marker only. 3, 6. Okay.
Oh, okay. Yeah.
Yeah. What do you think?
So it's gonna be like that, and the 6 is gonna be like.
Okay. Yeah. And then what's the resolve condition?
So it was larger than 6. X. Oh no. Yeah, it's larger than 6. Yeah, x.
Not quite.
Wait.
More than equals.
It's smaller than 6. So. It's from 3 to 6.
From 3 to 6, yes. So greater than equals 3, but note that, be very careful. This is greater than equals 2, so it's a solid dot, yeah? And then I draw a solid dot from here onward, right? And then less than 6 means it's a hollow, because it's not inclusive of 6 backward here. Yeah. Right? So the actual resolve condition, the part that overlaps is between 3 and 6, right? Oh, yeah. Is that part there, but be very careful. That would be 3 less than equals to
6.
Big X less than 6. Yeah. Make sense? Yeah. And in the case of discrete probability, so in this case, which is it 3, 4, 5, or 6 successes? This one would roughly be equivalent to 3, 4, or 5, right? Because it must be strictly less than 6. Yeah. Does that make sense? So if you were to do this one inside as whole number, so these are the only whole numbers that are between at least 3 and less than 6. Yeah. Does that make sense? Another example could look something like this. We'll do more of this next week, but another example could look something like this. X more than 3 and x more than or equals to 5. What do you think the result condition is?
So x smaller 3. So it's gonna be x smaller than 3. Wait,
that's greater than, yeah?
That's greater. Yeah, so.
Okay, do you know how I read the greater smaller symbol?
Yeah.
You look at the side of the symbol. Which side is greater?
X.
Yeah, right? So I read x and then greater than 3.
Yeah.
Yeah, so the other one, for example, this one, x smaller than 4.
Yeah.
Okay, so you look at from left to right, you look at the symbol from left to right. Like if it's smaller, then it's smaller. If it's greater, the bigger amount, then it's greater. That's it. Okay, so what's the resolve condition here?
Greater.
X is?
X is 5. Is bigger than 5.
Is greater than 5, like that?
Equal.
Greater or equals to 5. Okay, let's see if you're correct. 3, 5. Greater than 3 is this number.
Yeah.
Greater than equals to 5 is that number. So the only part that overlaps is the part after 5. And yes, you're correct. It is greater than or equals to 5.
Yeah.
Okay? So you get a question that is like, oh, given that something is more than 3, what's the probability that it is also more than 5?
Yeah.
Right? So you're only looking at the section 3 onwards. But then you're looking at the section that cross over with 5, which is the part that's greater than 5 only. Does that make sense?
Yeah.
Yeah. So the only weird case in this scenario is that if you have x equals to 4 and then x more than or equals to 1, it's discrete, which means that it's exact numbers, right? It's not a range, it's exact numbers. So the only number that fits is 4. Does that make sense?
Yeah.
Yeah, because one of the conditions is that x must be exactly equals to 4. Is that saying, you can borrow anything that's more than 20,000, and also you can only borrow exactly 25,000. So you can only borrow exactly 25,000. Does that make sense?
Yeah.
It's like you have a wide option, and then you have that exact number. The intersection is just that one exact number. There's no wiggle room in there. Okay, make sense? So that is, I guess, arguably is the hardest concept. You'll see this again in the next few chapters. The conditional probability. The formula is here. PRA given B is equals to PRA and B over PR of B. Okay. Applying that formula in the next few chapters will be the key to do well in the next exam.
Yeah.
It will appear again and again and again.
Do we have homework?
Huh?
Do we have homework?
No, not for this week. Yeah, let's take a break. You just finish your exam. Yeah, I'll go through this again next week, and then.
I mean, I don't mind.
Yeah, I mean you can just do the questions. The answers are there, right? So there's no official homework set this week, but feel free to go back and do everything. The more you do, the better. If you're aiming for 100% in the next exam, then yeah,